Huron. Reason this is probably very untraditional talk in this seminar. I actually couldn't attend this last semester because I was teaching on Fridays in Scarborough. So and as Rio said, I'm from mathematics. So first of all, the culture of giving talks is quite different. And second of all, if I understood correctly, this is primarily physics audience. So from my past experience, when I go to technical, 100% of the kind of audience gets lost. So I'm trying to be precise where I need to be and give kind of like the big picture idea otherwise. So let's see how this goes. And also there's like two aspects of this story. So this Vortex notes was already done like a couple of years ago, and unfortunately for this NISQ algorithm parts, there's not so much I can say publicly yet. That will change during this year, but we'll have to wait a little bit. But first of all, okay, it's not that one. It's not that one. Okay, let me see which one of these buttons works. Okay, that one works. Great. Okay, so my background, indeed, I am a mathematician. So I did my doctoral studies 2017 to 2022 at UBC, the second best university in Canada, right? And I work at the intersection of algebraic geometry. So that is the kind of study of the solutions to the polynomial equations, and topology, which is the study of shapes. So maybe one way to think about how these two they interact is that every time you take a polynomial equation, its solutions form some sort of shape, at least if you're working with real numbers or complex numbers. But in general, I was working at the area where the kind of main question could be summarized very briefly as saying how to understand number theory using geometry. So for example, how does this kind of rubber sheet geometry, topology, how can it help us to understand geometry? And maybe the number theoretic size you can kind of see from here. So this is a picture of an elliptic curve. And indeed, you can think of it as a subset of R2, like two-dimensional real plane. However, it's a very interesting question. For example, how many points do you have inside that curve where both of the coefficients are rational numbers? Okay, and this no longer is a purely topological or geometrical question, but has a lot to do with number theory. And if I need to even more justify why this is very serious mathematics, I can show you that the average person doing this looks something like this. It's mainly done by wizards. And by the way, this is a real mathematician. He's kind of the founding father, or was the founding father of modern algebraic geometry, until he ran into the mountains of France and lived as a hermit for the rest of his life. Yes. Okay. So now you could ask, like, what happened? Like, how did I go from this kind of number theoretical thing to physics? And here you can see a picture of me when I still had a personality. So I had long hair, listened to metal, and so on. And in year 2021, I was getting old enough so that if I don't do my mandatory national service in Finland, I cannot renew my passport, which is a little bit of an issue. So I had to solve that problem somehow. And of course, there's a standard way of doing it, joining the army. And it's not too bad. It takes half a year usually. But fortunately, I managed to do something a little bit more interesting. So I searched online for like interesting physics people in Finland, and I managed to convince this one professor, Mikko Möttönen, so that I can come to work on his lab instead. And it's a completely okay arrangement from the perspective of Finnish national service to do it this way. So the idea was that Mikko had done a lot of work on Bose-Einstein condensates, and especially what are the kind of topological defects that arise in those systems. And he thought, okay, I can do some useful work there for a year. Okay, so that's how I joined the group, which is called QCD Labs, and they even have a logo. Okay, and basically all this work about vortex knots is from this time when I was working in QCD Labs. Okay, so now let's go to the actual kind of scientific content, and let's talk about vortex knots. And I have 50 minutes, right? Yes. So first of all, I presume not everyone is kind of familiar with vortices, especially in quantum systems. But let's go at a very slow pace in some sense. So what are vortices? So everyone knows what is a tornado. Just air spins very fast. You don't want to go near it. It's bad news usually. So that is kind of a vortex in air, right? The air is spinning around a core. In the core, the air is kind of not moving. So if you manage to stand in the middle of the tornado, maybe you're fine if you don't touch the thing inside. But maybe more relevantly for quantum systems, you can think about another kind of vortex. So you can think about a wave function, let's say of a particle or something else, and you could have a point around which you go. Maybe the scalar phase of that wave function winds by some amount, or maybe it has to be some integer multiple of 2 pi I, because it has to go back to where it started. But that's basically the only limitation. And now, of course, that means that in the middle, there's no kind of way to assign a scalar phase value there without creating discontinuity. So one way to resolve this is that maybe the absolute value of the wave function goes to 0 there. So it has like 0 probability to be at the very center. Okay? And please, if something is unclear, please ask a question, because it's better to ask questions early than later when you're already completely lost. Okay, so these are kind of two very different systems, but they kind of behave in some sense in a very similar way. And this is what we call vortices. So for example, this kind of vortices you could even have in laser beams. This Laguerre-Gaussian laser beam basically looks like that. Or it could be some superfluid, or it could be some scalar Bose-Einstein condensate as well. Okay. What's imaginary? Oh, it's because, so this color here is basically representing the angle in the polar representation. So this is a field where every point you assign a complex number. So you can think of this color is just kind of recording the angle from the representation. So it's kind of a very simple, in some sense, vortex, because it's just the phase or the angle in the polar representation that is changing. And now, basically, vortices are kind of codimension too. So we live in a 3-dimensional world. So they form some sort of 1-dimensional object. And now, one thing that mathematicians like to do with 1-dimensional objects in 3 dimensions is to look what kind of knots they can form. So this is actually a real picture of a vortex in water that was created to be in the shape of a trefoil knot. So I think they basically just 3D printed the trefoil knot and then push water very fast through. So it started to spin around this kind of a vortex knot. Okay? So as you can see, these vortices can be formed in knots in physical systems. And this is actually a very old idea, because more than 150 years ago, Kelvin proposed that atoms are just vortices in the ether. Okay? So, of course, this is nonsense, because now we know there's no ether, and definitely atoms are not knots there. But it did inspire a lot of work on knot theory. So people started to classify knots precisely because they thought, now we can understand what are all the things in the universe made out of. We just classify knots, we understand everything. Okay, they classified knots, but they didn't understand everything in physics, but at least they understand knots. Okay. And so more formally, the framework I want to work with is the framework of ordered media. And okay, this is starting to look a little bit more mathematical, but so order parameter field, it's kind of it's a field. It's like a classical field where X here is basically the physical extent of the system. We live in three-dimensional world, so you might as well take X to be the maybe either a subset of real three-dimensional Euclidean space, or maybe you just take the whole thing. Okay, you don't have to do something very complicated, especially if you're working with down-to-earth systems. And now, of course, maybe you can even take two-dimensional system if you're working with very flat systems. People do that as well. But for this talk, real three-dimensional Euclidean space is basically all you need to think of. And now this order parameter field basically is an assignment of a field value at points of that system. Okay? I will soon give you an example what is an order parameter space, but it basically depends on what kind of substance is filling your system. Okay? But the important thing about this order parameter field is that it doesn't have to be everywhere defined. One way to think about it is that in the previous slide, we saw these two examples of vortices where at the core, at the middle, you couldn't assign anything, any kind of continuous value there. But we asked that it's continuous on its domain. So, okay, it might not be defined everywhere, but it's continuous everywhere else. So it doesn't suddenly jump. Okay? I think screen sharing is off. Okay, that's bad news. Let me try to fix. Oh, I think I dropped from the list. Is it on now?
No, I can't see. Can't you see your screen? I cannot.
It says I am screen sharing.
Hopefully it should turn me down. Oh, here it is. It's working now. Okay, yeah.
It's working? Okay.
It's good now. Thank you.
Excellent. I don't know what happened. Okay, so let's be very concrete and look at the concrete example. So I think the easiest non-trivial or interesting example is given by nematic liquid crystal, where basically, what is a liquid crystal? Well, nematic liquid crystal is a special kind of liquid crystal where basically it consists of this kind of molecules that kind of look like rods. Kind of very simple. And the order parameter field, in this case, would kind of assign to each point that it can the preferred local orientation of these liquid crystals or these molecules. And in this case, the order parameter space is very kind of easy to describe. So, of course, there's the different directions in three-dimensional space are classified by unit vectors in R3. However, these are symmetric. They don't have a head. So if you flip them 180 degrees, it's still the same shape, which means that we have to identify antipodes. So you take the two-dimensional sphere and you identify all the vectors on opposite sides. So it's a little bit hard to imagine. You cannot embed this shape into 3 dimensions anymore. But it's something that we mathematicians really know a lot about. It's the real projective plane. Okay? And in this case, vortex could look like this. So as you can see, I have kind of depicted the field in this case by kind of specifying at each point what is the orientation of these molecules at those points. And now you can see this kind of forms a codimension 2 singularity in the middle, because there's no way you can assign a direction here at the middle, because next to it, things are winding.
So when you say codimension 2, is this for any general order parameter field or specifically for problematic?
Oh, it's for anything. And okay, so the codimension 2 part is not important for any other reason that's what we call vortices. You can have singularities that have different codimension, but they have different names. So for example, you can have point-like singularities, and they are usually called monopoles.
What exactly do you mean?
So a singularity is,
What becomes single?
so singularity is kind of a point where this field is not defined. It doesn't have a specific value. So there can be like very stupid singularities. You could start with a continuous function and say, okay, I don't want to define this function at this point. And next slide, I'm gonna specify that what are the actually interesting singularities. And these are the kind of topologically essential ones.
But what happens if you take it out of the manifold? Say that I define a manifold in such a way that particular vortex exists.
Oh, then it would not be singularity in some sense. But I think in practice, if you have an experiment, you cannot take points of space outside of your experiment in some sense. So you could, for example, have a cloud of Bose-Einstein condensate, and in experiments you would see that maybe there's a point or maybe there's a vortex or a line where something weird is happening, and you can observe it actually in experiments. Okay. Oh, and this is a picture, like these nematic liquid crystals can really create this kind of interesting shapes when you overlay like a polarizing plate on top of it. So this is like a two-dimensional system, and you can kind of see the effect of the topological defects in these points. So this all corresponds to vortices. Okay. So now, not all vortices are interesting, because we want to look at those kind of singularities that are essential, that cannot be removed by local changes to the field. And this is actually essentially what is captured by topological vortices. So what is the idea? Okay, there's some math words over there. The idea is that, okay, you have your system and you have the field, and you look at a singularity, a point in the vortex maybe, and then you make a small loop around it, and you record what is the value of the order parameter field at each of the points. And when you do that, you will get some kind of loop at the order parameter space. So just for concreteness, I have chosen in this case just an example of a torus. So this is like a hollow donut. So there's a hole inside this one as well. And being a topological vortex just means that it will trace out a non-contractible loop. So in this example, A and B, you cannot contract, because if you try to make them small, they get stuck because there's a hole kind of preventing them from shrinking. So for example, maybe for A, it's easiest to see, like you can make it maybe be around here, but you cannot really make it contract all the way. However, the C is contractible. You can do, like, there's nothing stopping it from contracting to a single point. Okay. So if it looks like C, it's not a topological vortex, but in these two cases, it would be a topological vortex. A pinch singularity? Right, I think it would could still give you some sort of singularity, but I think usually in the evolution of the system, it will kind of disappear almost immediately. Whereas these topological vortices are kind of at least metastable. Of course, they still have energy, and then I think that the matter may actually change phase, which will destroy all the structure. But they live long enough, like they live, I think, well, long enough for the experimentalists to actually take a picture. I don't want to say numbers because I will get them wrong. I haven't done a single experiment in my life. That's not a good sound. Okay. Okay. And the non-contractibility just means that basically you cannot make a local change around this field, like something small modification here to fill in the singularity. You have to do something more local. Okay. And up to homotopy, which just means continuous deformation, these different vortex types can be understood with standard tools of topology. Okay, so there's a formula for the vortex types where this is the so-called fundamental group, and then you don't really take the fundamental group, but you take the elements there up to conjugation. It's kind of like matrix conjugation, but in general groups. Where the fundamental group just means you look at all the loops, the homotopy classes of loops, starting at a single chosen point. This has an algebraic structure given by concatenating loops, because you have two loops from the same point. You can first traverse the first one and then the second one. And this is some algebraic structure that, given a shape, topologists really know many tricks to compute this thing. It's very computable. Simple examples, if your space is just a circle, then this group is just the integers. Just counts the winding number. How many times did you go around the circle? To which direction? And for this torus, it's actually integers times the integers, because there's kind of two independent winding numbers happening here. How many times did you go this direction? And how many times did you go to this direction? Okay? And in general, I think all these systems that are kind of relevant in, let's say, Bose-Einstein condensates or other very concrete systems, mathematicians can just compute this thing like this. Like, you don't even have to be a mathematician. Like, some physicists also do it, but in some papers they're a bit wrong, as I noticed. Okay. And now, okay, we know what is topological. Now the interesting part is non-abelian vortices. So the non-abelian vortices are topological vortices, or these essential singularities, in a system where the order parameter space is non-abelian. So it's not commutative. So a simple example that is relevant for this talk is the case where the fundamental group at least contains this group QA8, which is relevant, for example, in the cyclic and tetrahedral phases of spin 2 Bose-Einstein condensate. Okay, that's a lot of words, but it's something that people can actually realize in laboratory. Moreover, this group would also occur for special kind of exotic liquid crystals. Okay, so the group is very simple. It's just all the unit standard quaternion, so plus minus 1, plus minus I, plus minus j, plus minus k. I think we all know that this is not a commutative group, because the group operation is given by multiplication. And I times j is minus j times I. It's not the same as j minus I times I. Okay? And now, one way to think about this is that it arises in system where the order parameter space has something to do with tetrahedral orientations. So at each point, the field kind of gives you one orientation for the tetrahedron. And in that case, for example, in that case, this the way to think about it as members of the order fundamental group of the order parameter space is via this kind of paths. So these I, J, and K are when you have 180-degree symmetry of the tetrahedron and you perform this loop, like you wind around when you go around this loop. Yes, you had a question?
Yeah, sorry, it might be hopeless, but I thought better to try now. I don't actually know what the fundamental group of the system means, but I do work with spin through Bose-Einstein condensates. Is there any words you could offer to us about in what sense the spin 2 BEC is related to the quaternion group? What does this group describe about that physical system?
Well, are you familiar with like the order parameter space of spin 2 BEC?
Okay.
At least in some phases.
So at every point in space, I have some 5-dimensional.
Exactly. And now in these different phases, you actually don't take the whole 5-dimensional system, but you're restricted to like a sub-manifold inside there. Okay? And these are kind of special loops inside that sub-manifold. So one way to think about it is that they are like, you can also associate some 5-dimensional complex vector to these things. I did not do it because I think in one of our papers, we actually have written them down. It's not pretty.
It's a topological singularity. It's not like it goes away.
It doesn't go away if you restrict to a certain phase of the system.
But without the restriction?
Without the restriction, then it can go away. Yeah, so because if you don't have the restriction, then I think there's too much freedom. You can just kind of take it out. You can deform it in such a way that it goes away.
If there's something about it being distinct, like, you know, I look at the quaternions and I think we're talking about the Pauli group. Is just any SU2 going to have a similar way, or really needed to be this restricted spin 2?
Oh, so spin 2 was just because that's the simplest, the lowest spin number where we have this kind of group occurring. So unfortunately, spin 1, the phases of spin 1 BEC.
I was even think
Right. So it just turns out that people have studied these different phases of spin or BECs quite a lot. And we just went through all the papers and see, okay, when do we start seeing like interesting groups?
But the point is, it's not just SU.
Well, it is actually related to SU2, but for some reason, in the spin 1 case, you cannot make this SU2 to kind of have these kind of things, because SU2 is the unit quaternions, right? Like, so actually everything here is very, like every group you can get in spin or BECs is kind of a subgroup of SU2, a discrete subgroup. For some reason, for low enough spin, you cannot have that kind of groups occurring. Yeah, I don't know if I answered it, but I tried. Yes.
Just to make sure. So this tetrahedra is not actually the like a representation with the 5 dimensions at each point, but it's a subspace of it.
So actually, in general, these tetrahedral orientations are almost the whole thing, but they forget the scalar phase. So if you also take into account the scalar phase, then that's completely, at least in this one of the phases, so the tetrahedral phase. Oh yeah, okay, maybe that's what you were asking. Like this will give you a subspace in the full 5-dimensional vector representation, but there's like a subspace that corresponds to essentially very closely to these tetrahedral orientations. Yes. Okay. Do they look identical? Because I remember earlier I've given a talk where I included the wrong picture. That is very correct. Okay, it should be a different. Yeah. So because there's like K is different, right? And I think, okay, because they look so, if you look very quickly, they look the same. So I think, because I basically just took a screenshot from my old slides, and okay, I think there was a mistake there. Okay, but that's a very good point. So it should be different. Because there's basically 3 ways you can like choose the rotational axis. So one of them is missing here. Okay, so this is the visualization. And oh no, and one of the interesting properties of these non-abelian vortices is that this non-commutativity can obstruct vortices going through each other. So these are from some paper that simulates, actually, I think they are even studying like spin or BECs in this paper. And the idea is that, okay, these vortices essentially correspond to some elements in here. So maybe this one corresponds to I, and this one corresponds to J. And when they try to go through each other, there's a topological obstruction, which kind of creates this extra vortex between them, which is kind of energetically unfavorable. And if
Basically, no.
or what can you repeat?
So essentially, you will have to form knots, non-trivial knots.
Yeah. So yeah, for example, like this kind of helps you keeping the knot structure together because they cannot just freely pass through each other. Okay. And now the question is, okay, can we turn these non-abelian vortex knots into, or can we turn these non-abelian vortices into knots? That was the question I wanted to think about back then. And what makes this interesting, what is the problem, is that the topology of the order parameter space and the topology of the knot interact in a non-trivial way. So, and this only happens when you have non-commutativity in this group. If this is commutative, then it's very easy. Like this is very simple.
So some of your studying are suggesting that when you have this non-commutative structure, then inevitably you would entangle the system. But in the case of abelian, you can actually, because you can unknot them. And if you think about in a quantum sense, it would be like the pure state, while the knot one will be an entangled state.
Yeah, I think so. And as you can, like in the previous slide, I showed what happens when you have non-commuting elements. So if you're abelian, then you don't have those. And then they can actually just pass through each other without any problem, or they can reconnect maybe even. Okay. So this problem is what makes it mathematically interesting. And there's at least 2 questions to consider. So if you fix a core topology, so let's say you want to understand what kind of fields could be around this trefoil knot, how can you understand it efficiently? Because it's it's not so easy to write down continuous functions on the complement of the trefoil knot in some complicated 5-dimensional field. Is there a better way to understand them? And the second question is, are some knot structures kind of resistant against like being destroyed by these reconnections and strand crossing properties? So for example, and okay, I couldn't find a good picture that looks nice, so I drew this with my tablet. But the idea, like one thing that often tends to happen, for example, these water vortices in knots, is that 2 of the parts of the vortex get close to each other and they reconnect. And so they go from this to this. And now this is just actually a simple loop. Like this doesn't have any topological structure. Okay. So the question is there some structures that are resistant against this kind of decay? And we'll have answers to both, but the answer to the first one is how to understand this. Like, you have a question? Right, so I would call that reconnection. So it's kind of like, oh yeah, maybe people are not familiar with the knot diagram. These are not actually cuts. This is just denoting which part goes under which part. So it's like this one used to go under, but now like this part connects to this one, and this part reconnects to this one. And this is how it forms a picture like that. Yes.
I have a hard time understanding this question.
Right. So,
Or-
oh yeah, so core topology just means, okay, I fix some sort of a knot, and I understand what kind of vortices can be around that knot, what kind of fields you can make around that knot. Okay, so the knot kind of fixes where the singularity is, and now you're interested in what are the different fields around it. And now this question has a very nice, the first question has a very nice solution. So in this assumption, this is, okay, you have to look at the higher homotopic groups a little bit. It's not so important what it is, but this condition is satisfied for spin 2 BEC and also for these exotic liquid crystals. And in this situation, you can completely capture the homotopy class of the order parameter field. So you understand it completely up to continuous deformations by a colored link diagram. And okay, there's again some words over there, but let's see what they look like. So let's look at a very concrete example with this same group, is that we can assign, depending on which group element we take, a bicoloring to the vortex that kind of records which element does it correspond to. There's two colors for the reason that you want to record is this way I and this way is minus I, because I and minus I are different. You have to record it somehow. That's the reason for the bicoloring. And I have completely ignored the plus minus one because it doesn't really contribute anything interesting to this story. Okay? So the idea is that every time you have this kind of knot diagram and you label all of the arcs by a group element, and a very concrete way to do it is to use this kind of colors. And you will do that. And okay. So in that case, whenever you have a crossing, the direction of the bicoloring will flip if you go under a strand of different color. So you can see this is a gray one going under a red vortex, and this will flip. So this is something that's completely dictated by the fundamental group. These rules, you can just look at the group structure and you will get them. And then if you go under a strand of the same color, nothing happens. So the point is that if you make any colored diagram that respects these crossing rules and where every arc is colored by one of these colors, then that describes a unique kind of tetrahedral orientation field around this singularity up to homotopy. So let me just emphasize that this field is some very continuous, very infinite data, very complicated data, whereas this coloring is very discrete. It's very simple, and it makes it much easier to understand what kind of structures are essentially possible in this system.
So does it mean that, let's say, this top ring is like red? I make a loop around it, and my field is going to make a loop corresponding to this like I momentum.
Yeah, exactly. So if you go around this core, it will make the kind of the tetrahedron will turn in one direction. Whereas if you go around here one, the tetrahedron will kind of turn across another axis.
The pattern below the blue it's reversed. So the binding will
Where?
in the fragment below the blue, the red fragment below.
This one?
Yeah.
Yes, it's reversed because of this crossing rule. Because this is a different color, so it has to flip And this means that, okay, if I go around here, and if I go like this, they're going to, the rotation is happening in a different direction.
There's some distance.
So the only discontinuity is when you go under another. And okay, it's very confusing because I haven't explained it all carefully, but all of these things you can get by you fix a base point that lives over your picture. And the colors you get from going from this base point to here and then going under and then coming back directly. So you can see that when you go from here to here, there is a discontinuity because you cannot deform the loop that's based here and goes under here to this one. Okay? So in some sense, like this is capturing more information than just the pure like vortex type, but it's something that you have to consider in these more complicated systems. Okay. This picture also makes it clear how to like think about this evolution of the core topology. So remember, non-commuting vortices, they cannot just simply pass through each other. And the way to think about it is that in this framework, non-commutativity means that the coloring, something weird, something discontinuous happens here. And they cannot cross because if this gray vortex comes forward and is in front of the red one, then there would be a discontinuity. But the only discontinuities that are allowed is when you go behind another vortex. So this is the reason why this cannot simply just cross each other. There has to be something that forms between them that takes care of the discontinuity. But it also suggests, okay, this is very annoying, this thing. Okay. So in general, this also explains what kind of core topology evolution we can have in the system. So in this case, it's very easy to classify all of them. So I have here the evolutions for the gray vortices, but the blue and the red, they have exactly the same picture. So for example, this kind of configuration, because there's no flipping here, they can just simply pass through each other. Or they could reconnect. So this one could go here and this one could go here. And similarly, if you have a picture like this, it could evolve to a picture like this. So this is just, basically you can do any kind of evolution that kind of doesn't introduce discontinuities in the coloring is allowed.
Just make you aware of the time.
Yes, I have 7 minutes.
Yeah.
Yes. So the second thing that we consider is this paper is, okay, a non-abelian vortex configuration is topologically protected if you cannot destroy the knottedness of the system using these color conserving local evolutions. So let me again give you an example. What we don't want to happen is this kind of a loop. So there's two things are linked together. They're linked together like twice. So if they were actual strings, you couldn't pull them apart. But in this system, these strands could get closer and then reconnect. And you have to squint a little bit, but these are no longer linked. You can just pull the gray one out and they will separate. Okay, so topological protection means you cannot do this. You cannot make it into a boring structure. And roughly, this is kind of things that cannot be destroyed in the physical evolution of the system that does not destroy the face of the system. And an example of a structure like this is already I showed you this structure before, and this you cannot destroy. Okay? So, okay. And how does one prove this thing? So it's kind of simple. So to prove this topological protection, I need to construct invariants that has two properties. So first of all, in this evolution that can happen, the invariant should remain the same. And second of all, on any configuration of simple unlinked loops, it should obtain trivial value. So these are usually take values in some sort of group, so all groups have trivial element. And in this case, non-trivial invariant means topological protection. So from this kind of decaying into simple unlinked loops. So you cannot destroy the knottedness of the vortex structure by using this evolution. So here we do have examples of three structures, and I have even shown their invariants. So there's two kinds of invariants. So the easier one of these is the L invariant, which is the linking invariant. And it's computed by saying that you pick any two colors you can choose. They have to be different colors. And then you compute the total linking number between colors of, let's say, gray loops and red loops. And you take that number modulo 2. So either 0 or 1, depending if it's even or odd. And this does have both of these properties. And it's easy to compute them for all of these. And the answer is, in both cases, 1. And in the center, it's 0. So unfortunately, this is not enough to detect all the possible protection. But you need something a bit more complicated, but it's still something that you can compute from the picture in an easy way. Like it will take maybe 20 minutes to learn how to do it. Okay. Yeah, I'm starting to lose my voice a little bit. I guess it's going around. And interestingly, this is also a complete classification of these kind of vortices up to this kind of equivalence. Okay?
U8, so does it correspond to your SU3 compliant?
SU2?
SU2.
SU3? I think it could also occur in some SU3 systems. But mostly the things that we studied are very closely related to SU2. Okay. So in the last remaining minutes, I think I will have to end at the vortex knot story. I just want to emphasize that this method is completely general. It's just different systems have a different order parameter space, and therefore you get different colors and different crossing rules. So I just include here two examples of other systems that we studied. So here is the case where the fundamental group is a permutation group on 3 elements. And in this case, these are the kind of possible structure that can happen. Okay, you just need to construct a different invariant, and in this case, okay, it's called I. And then in the tetrahedral phase of spin 2 BEC, you also need to consider this extension of the Q8, which also includes these kind of quaternions. And in that, once you allow these more general colors as well, more general group elements, you get a lot more other types of vortices. So for example, you get this kind of trefoil knot that was actually not possible with Q8. Okay. So I think this is a good place to end because I am running out of time.